All right, welcome. It is Tuesday, November 3rd, Election Day. Thank God. One way or the other, it's over. That's the best part about Election Day. Okay, and so we're reviewing the properties of ionic compounds. And so in ionic compounds, we know that it's an element, a non-metal. Let's try that again. It is a metal combined with a non-metal. What did we just say about the electronegativity of metal?
Low.
It's low. Electronegativity of nonmetals are high. Therefore, you have a big difference. So what happens to electrons? They transfer, forming ions. What holds the ions together? Coulombic attractions. And I just said there's a new name for, an alternate name for Coulombic attractions called electrostatic attraction. It's a static attraction. It's the buildup of charge, positive on one, negative on the other. Let's go cross-curricular to English. What does the word static mean in this case?
Not changing.
Not changing, or I thought you said a word.
I didn't say.
Not changing or stationary. Okay? If something's static, it's not moving. Dynamic means it's changing. So dynamic equilibrium means that the concentrations are staying the same, but some dissolves and some crystallize. It's constantly changing. Whereas something that's static is stationary, it's not moving. So static electricity is a buildup of charge, positive on one end, negative on the other. Unlike electricity flowing through the wires where the actual charge is moving. Okay? So, we have static electricity or Coulombic forces holding ionic compounds together. What do we call the energy that you have to put in to break them apart? Say that again loud.
Lattice energy.
Lattice energy. Okay? Now, as a result, what type of melting points do ionic compounds have? High or low? High. So at room temperature, almost all ionic compounds are going to be in what state? Solid. Okay? And it's going to take extreme temperatures generally to melt them to get them to even be a liquid. So why then in this salt crystal will it conduct electricity in the solid state? Why not? Okay, let's just talk about words here, specific words. Okay? What makes up an ionic compound? Ions. Are they charged particles? Why can't they conduct electricity? They can't move because they're held rigidly in a crystal lattice structure. Okay? But we want to use the word ions are held rigidly, not molecules, not atoms. The ions are held rigidly in place. Okay? And cannot move. So how do we make them move?
Dissolve.
Put them in water, which what's the fancy word? What happens to them when they break apart? They dissociate, okay, and form ions. And then what's another way in which we can break the ions apart? Melt them. Add the lattice energy and melt them. Okay? And one other characteristic you need to know about was that they are brittle. What happens when you change the structure of the lattice?
Like breaks.
It does break, but why? Say that again, Kritika.
The charges are like the same, so you probably try.
And so what happens?
It breaks the little crystal.
Because like charges repel one another. Okay? So they're going to break. So if I'm trying to pull straight across like this, it's pretty hard. But if I just can turn it just a little bit, make positive get next to positive, negative gets next to negative, then it comes apart real easily. Okay? And so ionic compounds are brittle because when you change the crystal structure, positive gets next to positive, negative gets next to negative. All right? Now, that's pretty much all you need to know. And we've talked a lot about Coulomb's law and lattice energy and being able to tell the difference between melting points based upon the product of the charges and the size of the ion. Okay? But you definitely need to be aware of that and be able to do that. Is everybody good with that? Okay? So that's ionic bonding. Metallic bonding, what's the key phrase? Cation surrounded by a sea of free-floating valence electrons. Okay? Now, their melting points vary widely, but we want to be able to describe, explain two properties. Why are metals malleable? Why can you change them? You can't change an ionic compound, but why can you change the structure of a metallic substance? Because the electrons, what about the electron? What makes this break apart? Light charges being together. But because we have a sea of free-floating valence electrons, okay, they move, when the positive moves, the negatives can kind of move with it and fill in between and keep positive from getting next to positive. So you can rearrange the shape because the electrons are much more fluid. Okay? And then why, obviously, do metals conduct in both solid and liquid state? Because the sea of free-floating valence electrons. Electricity is the flow of charged particles, so they can flow one to another. Okay? So we need to be able to describe those characteristics of ionic compounds and metallic compounds. Then we went into covalent. And what happens with electrons in covalent? They're shared because we have two nonmetals whose electronegativities are much closer. So one doesn't have the ability to pull the electron completely away. So they come up with this novel idea, hey, let's just share. Okay? And so they share electrons to form what? How many electrons do most atoms want to have around the central atom, or around each atom? 8, the octeteral. Okay? So they're going to gain, lose, or share electrons to get to that 8. So everything in the world, okay, everything in the world runs, is energized by atoms wanting to get a field octet. Electrons going from one thing to another is what, makes us live. It's the chemical reactions that take place. It's all about the field octet. Okay? So, I went into a little bit yesterday of H2SO4. What is the oxidation state of sulfur in H2SO4? Plus 6, because we know oxygen is always -2. We have 4 of them, so it's -8. Hydrogen is +1, so we get +2, which makes sulfur +6, because we know the sum has to add up to 0. For any neutral molecule, sum of the oxidation number is going to be 0. What does that +6 mean? 6 electrons involved in bond. It doesn't have really a +6 charge on it. Did it lose 6 electrons? No, it's sharing the 6 electrons. And again, if we want to just follow the electrons, sulfur has 6 valence electrons that we would do the Lewis dot structure like that. You can put an oxygen and then the hydrogen, an oxygen and the hydrogen. But now we have these 2 spots, so how do the oxygens bond there? Oxygens move their electrons, and both electrons of the shared pair come from sulfur. And what do we call this? Doors open. What do we call this type of bond? That's a coordinate covalent bond. Okay? And so would this one be. But once formed, what's the difference between this bond and this bond? Nothing. Okay, so we generally don't worry about the source of the electrons, but that's what oxidation state tells us, that sulfur has 6 of its electrons involved in bonding. Okay? Which is why the nonmetals can have that plethora of possible oxidation states, because of oxygen's ability to bond with these lone pair. When they combine with just about everything else, they're going to be in the -1, -2, -3. But when it's combining with oxygen, because of the different ways in which it can combine, it has the varying oxidation states. So, but if you always look, it always goes in 2s. Okay? So Bromine has a maximum, they have 7 valence electrons, so it's normally -1. But when it's with oxygen, it can be in the +1, +3, +5, or +7 as well. But those aren't as nearly as common. Sulfur has 6 valence electrons, so its highest oxidation state is +6. It can only have 6 electrons involved in bonding, that's all it's got. Okay? But it can also be 2 and 4. It just varies. Okay? And then it's obviously -2 as well when it combines with just about anything else. Any metal it's going to combine with, it's going to be the negative oxidation state. Phosphorus is 3 and 5. You can, again, use the 3 electrons in the P, or all 5, the S and the P can use all 5, but it's just the way that it bonds. Okay? So, that was oxidation state. We need to be able to calculate the oxidation state. So if I gave you KMnO4, don't say an answer out, but what would be the oxidation state of manganese in this? I had to review a little bit because Friday's video where we talked about ionic and metallic bonding got corrupted and I couldn't post it. Mn's number 25. This should be a 10 to 15 second max problem once you know what you're doing. What's the oxidation state of potassium always?
1.
+1. It's the only one it can be. Group 1A, +1. What's oxygen? It's almost always. -2. But we have 4 of them, so -8. That adds up, it has to add up to 0, so manganese must be +7. Okay? Now, if it were Cr2O7, 2-, what's the charge on oxygen? -2, so it's going to be -14. So what's the total positive charge? +12, but since we have 2 of them, each one must be +6. Because it has to add up to the charge on the ion. We're good with that? That needs to be something that you guys can just do easy without thinking. Is there any confusion? Gonna have some life today. Come on now. Gonna have some life. It's election day. Everybody's a little nervous. What's gonna happen?
Can we do another?
One more? Uno más? Let's say PO4 3-. Now, one way to check your answer, if you got it right, is all the possible oxidation states are above the symbol. So if the answer you got is not one of the little black numbers above the symbol, then you might want to recalculate. Okay? Because those are the only possibilities. So what do we know oxygen is? -2. We have 4 of them, so it's -8. Has to add up to -3. So phosphorus is +5. It means it has all of its electrons involved in bonding. Now, just because I can't help myself, if we were to draw the Lewis dot structure for this, let's do it in terms of electrons. Phosphorus has 5 valence electrons. So if I put, you always want to go with the unpaired electrons first as far as forming bonds. So I'm going to put my oxygens in here, but each oxygen will still be deficient 1 electron. Okay? So how do I fill that 1 electron on each one? What does this tell me? I get 3 extra electrons, right? So I can put my 1, 2, 3 extra electrons there. Okay? And then where's my fourth oxygen go? With a coordinate covalent bond over here. So how many of phosphorus's electrons are now involved in bonding? All 5. Okay? That's what that means. Doesn't mean it lost 5 electrons. It doesn't mean it has a +5 charge on the phosphorus. It just means you got 5 of its electrons involved in bonding. The less electronegative element is always positive. The more electronegative element is negative. It just tells how many electrons. Now the interesting thing on this is oxygen's still in the -2, and it gets credit for both of these shared pair right there as well, because it's forming that bond. All right. That doesn't give us a true indication of charge, so we came up with formal charge. And that's what you did at the end of class yesterday. You went through that sheet and you did the formal charge. What was the only one that changed? The first one. That was kind of wrong, but it also got you the ability to practice formal charge. So let's just look at that first one, SO3. Okay? When you originally drew the Lewis dot structure, it looked like that. Okay? Now, it doesn't matter which one you have a double bond on, doesn't matter if you did it as a T and the shape, just you have 3 oxygens around, a double and 2 single bonds. Okay? So, if I'm going to do, this oxygen is going to be different, so that's oxygen 1, these are going to be oxygen 2s. So what's sulfur? How do I do the formal charge of sulfur? Valence electrons, which is 6, minus
1/2
of,
of the
how many are there? 2, 4,
8.
6, 8. 1/2 of 8 minus how many lone pair? 0. So that's going to equal plus 2. I was kind of wanting to subtract 8. Okay? So oxygen 1. 6 minus 1/2 of 4 minus 4 is going to equal 0. We like that. We like zeros. And then oxygen 2. 6 minus 1/2 of 2 minus 6 is going to equal -1. So we're not minimized. Okay, we want to try and get everything to 0 if possible. We have 2 of these. Okay? So we have 2 of the -1s. How do I make a -1 become a 0 and a +2 go down towards 0? Double bond. Steal the electrons from the -1 and share them with the +1. So pick any 2 electrons in here. So now what's this oxygen right here? If I just stop, what's this one going to be if you recalculate? 0. What's this going to be now? +1. Right? Without recalculating, without having to redo it, we know it's one's going to go up by 1, one's going to go down by 1. So I need to do it one more time to there, because now everything is 0. Now, according to formal charge, this would be the best Lewis dot structure. Now, the reason why it's a challenge is because how can sulfur form all of those double bonds? Our present bonding theory isn't going to really allow for that. Okay? So, by finding out one thing, it kind of creates problems in the other thing. We definitely don't have all the answers yet on the bonding. Okay? We being mankind, humankind. Okay? We just don't have it. Okay? So this was the only one that changed. Does anybody have any questions? Now listen, very, 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 very important. If a problem ever asks to do a Lewis dot structure, complete the Lewis dot structure, whatever, always do it just in terms of the octet rule like we had it originally with just 1 double bond and 2 singles. Okay? Only time you mess with formal charge is when the question specifically asks about formal charge, which is about one question every 3 years. Okay? So it's not a super big deal, but you have to be able to remember this formula. Yeah, that's not on the equation sheet. Any questions on formal charge? That's kind of a review of everything that we've done so far in this unit. We all good? You awake? You guys need to go to Starbucks. You need to get you some coffee. You broke, is that what you said? Yeah. I can relate to that. But I just drink my Diet Mountain Dews. Get them for 30 cents a can, 50 cents a bottle. Stay fired up. Come on, I'm the old guy here. I'm the one supposed to be tired. Okay. So now what we want to do is get into some really nitty-gritty chemistry. I know, I advise somebody can put this head down. Okay, we're gonna get into the mechanics now. How in a single, double, triple bond, how do the bonds actually form? How do they share electrons? What are the mechanics of the atoms coming together? What do they do? What makes that bond? Okay, so.
Yes.
Is it fun for
Nobody
nobody?
can find my house.
You think so? You should get a sheet of paper. Probably.
Yeah.
Nothing I can memorize in my head. You know, my vote counts as 700 million American people.
700 million out of the 350 million actual people.
I choose vote.
Okay. We ready? There are two ways in which orbitals actually overlap. The first type is called a sigma bond. And the Greek letter is a lowercase sigma. It's an O, little O with a tail on the top. Okay? A sigma bond. This is a direct overlap. Of any and all types of orbitals where the overlap lies on a line between the two nuclei. Sigma bond. So when I'm looking at a sigma bond, if I take an s orbital with the nucleus and another s orbital with the nucleus, this is where the orbitals overlap. So the electron from this one and the electron from this one, this is where your electron density is going to be. The electrons get trapped. This electron is being drawn to that nucleus. This electron is being drawn to that nucleus. They end up being right in the middle. If you draw a line between the two nuclei, it touches the overlap. Now, you can have two p orbitals. That's the nucleus. This is the nucleus. Here's the overlap. Again, this electron is being drawn to that nucleus. This electron is being drawn to that nucleus. Well, this electron is being drawn to that nucleus. But if you draw a dotted line, the overlap is between. This is a direct overlap. This is maximum overlap. These get maximum overlap. It's the first bond between any two atoms. So if it's a single bond, it is a sigma type bond. The first bond between any two atoms is always this type. Now you can have an S and a P overlap. Here's the overlap. Notice again the line drawn between the two nuclei. touches the overlap. All orbitals form sigma bonds. We're gonna SP, D, F, and then we're gonna find, maybe today, probably today, we're gonna find about hybrid orbitals as well. They're new molecular orbitals, different things, okay? All orbitals can form sigma bonds. First bond is always a sigma bond. You get the maximum overlap, which makes it the strongest type of overlap. Okay? So, make sure I'm in the screen. Number 2
You are.
is a pi bond. Another use, Greek letter pi. Okay? A pi bond. Thank you. This is an overlap of p orbitals. Where the overlap, what am I going to say? What am I going to say next? Where the overlap does not lie on a line between the two nuclei. Does not lie between the two nuclei. Okay? It's a side-to-side overlap of p orbitals. And that's the key. P orbitals only. So we get the overlaps up here, the overlaps up here, here's the nucleus. When you draw a line between the two nuclei, the overlap is not between, does not lie on a line between the two nuclei. Now only p orbitals can form pi bonds. sp, s, d, f, hybrid orbitals, no other orbitals can form pi bonds. Only these. But the second bond of a double bond and the second and third bonds of a triple bond are always pi bonds. So there's two different ways. So when we're looking at what's forming and how things form, we have to first off understand how the orbitals overlap. There's just two different ways, sigma bonds, pi bonds. Now this is very simple to figure out, okay? On my test, the AP test, you don't have to draw this out and give the definition or whatever, but they may give you a compound, something crazy. Okay, something that looks like this. And we want to say, how many sigma bonds and how many pi bonds are in this compound? Or, sometimes multiple choice, how many pi bonds are there? Well, the first bond between any two atoms, if it's a single bond, what type of bond is it?
Sigma.
Sigma. So we have sigma, 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 sigma. And then when you have a double bond, the first bond is always sigma, but the second bond is always pi. Sigma, sigma. What about this one then? What are we gonna have on a triple bond?
Sigma pi pi.
Sigma, pi, pi. Sigma, sigma, pi. That's a sigma down there. Sigma, 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 sigma. Okay? So, when we get into hybridization here in a second, we're gonna look more about the reason why we have to have these pi bonds and the only p orbitals and all of that. But the reality is, as far as being able to identify, you just need to know first bond is always sigma bond. Second and third bonds are always pi bonds. Okay? So that's easy. That's an easy money multiple choice question. Just go in there. Okay? Good stuff. Deep stuff. By the way, who just sent me? Oh, you guys remember Juan, Lupita and Juan,
Juan Luis?
Juan Luis, yeah.
Yeah.
What's his last name?
Contreras?
Contreras, yeah. Anyway, he just sent me an email last week thanking me, you know, just saying that he's making one of the highest grades in his general chem class. You know, can't quite remember where he's going. It's an elite school, I think, that he's going to. But he was just, you know, saying that, you know, he felt very prepared and that he's able to help other people, and you know, so this what we're doing here is definitely college level, okay, foundational stuff for chemistry, which is going to prepare you and let you just be head and shoulders above the average person coming in to a chemistry 1 class in college, okay, which is why we're here. I know you want to get the 5 on your GPA, okay? But the reality is we're here to learn chemistry and understand, because some of y'all want to be doctors and you know, nurse and practitioners and physicians, assistants, and chemical engineers and all of that. And so you're going to end up taking a lot of chemistry to understand how the world works. We're getting into the good stuff. We're no longer up here with the chemistry 1 stuff. We're getting to the meat and potatoes. All right. So, how do individual atoms bond? Oh, and by the way, that made me think. I always say bond, chemical bonds, you know, like James Bond. Sean Connery died yesterday, or the day before. He was the best James Bond ever. Some of y'all don't even know who that is, which is sad.
Well, I like,
He was the first.
I think it was it Sean first? Yeah.
I miss Juanito.
I always tell people that my hair is not naturally gray. I just put in my Sean Connery highlights because I wanted to, you know, kind of look like him, you know, with the gray. But most people don't believe that that's the truth. And you know why they don't believe it's not the truth? It's not
I
the
wonder
truth.
why.
Okay. Now, that was an introduction to get your appetite whetted for the real good stuff. Okay? Because here comes the real good stuff. It's a thing that we call hybridization. Okay? Hybridization. If I take a red rose and a white rose and I hybridize it, what do I get? A pink rose, right? Or it could be a polka dot. Okay? So if I say a pink polka dot rose, is it a white rose with pink polka dots? Or is it a pink rose with white polka dots? If I say a pink polka dot rose, this is just one of the mysteries of life that, you know, I always ask, because there's that, have you ever heard the song, the itty bitty teeny weeny yellow polka dot bikini? Okay, I think they had it on an old Navy commercial at one point too, but, you know, So when you think of that itty bitty teeny weeny yellow polka dot bikini, what do you envision?
The polka dots are yellow.
The polka dots are yellow and the bathing suit's some other color?
Yeah.
No, it's
No,
a
it's
yellow.
yellow with
bikini
polka
that's-
dots.
See, we all see things differently in there, so that's always a fascination for me.
Yeah.
Okay? But that's neither here nor there, that's just my randomness in my brain trying to figure out life and how we process things differently, okay? The key is in that hybridization, it's a mixture of the two, right? Now, what is the definition of an orbital? Okay, the place where you're expected, most probable place to find an electron. Okay, what's it based on? Math, but the math is explaining what determines, what property of the electron determines where it is, which orbital it's in, which energy levels it's in. I just gave you the answer. Energy. Okay? Energy. The energy of the electron determines where it's going to be, an s orbital, a p orbital, a d orbital, second energy level, third energy level, fourth energy level. It's all based on energy. So all of the quantum theory, quantum means specific amount. The electron can only have specific amounts of energy. And given that energy, it's going to be in a certain wave pattern that's going to be at a certain distance from the nucleus, because that's the only place the standing wave pattern can form with that particular energy. Okay? That's pretty complicated, but we're just going to trust that it all is true. Okay? Because I don't understand the math to be able to argue with it. So, when we have atoms that begin to combine and get closer to one another, their electron clouds begin to interact. And so you're going to change the energy of the electrons because they're now going to have repulsive forces. They're going to start being attracted to this nucleus. These are attracted to that nucleus. So the energy of the electrons all change, which means where they're going to hang out changes. So if we take an s orbital and we combine it with a p orbital, our hybrid is going to be a mix of the two. We're going to end up getting something that looks like that. Okay? Now, this part is so insignificant, we pretty much just leave it off and ignore it, okay? So it's really just going to be one fat side of the p orbital. Okay? It's going to have more energy than an s, less energy than a p. It's kind of like the s and the p, they just kind of combine their energies and then divvy it up and put it all into this one hybrid orbital. Okay, all of our hybrid orbitals have basically the same shape. It's only s and p orbitals are involved in hybridization. It used to be thought that the d's were, but evidence has shown that they're not. So your s and p's. So let's look at carbon. Okay? Carbon's electron configuration is 1s, 2s, 2p. This is what we say it's its ground state. Okay? Now if I was to draw the Lewis dot structure for that, it would have to look like that. If it was accurate, right? Now normally we just draw 4 dots that single around because we get to the end point, but now we're going to find out why do we get to that end point. Okay? Rather than just somebody saying, this is what you do with carbon, you put 4 dots. But this is, this is when we draw arrow diagrams, our Lewis dot structure ought to match up to our arrow diagram. Right? But it doesn't. But if I was to bond right here, and I want to make carbon and hydrogen, I want to make CH2, I could put a hydrogen in here, I could put a hydrogen in here, okay? But I would get CH2. Now, does carbon have a filled octet? No. So it's really not stable, and we find that CH2 never exists. CH4 exists. Methane, that's what comes out of here. This is methane gas. CH4 is the compound that forms between carbon and hydrogen. So scientists say, well, how can carbon form CH4? How can we have 4 single bonds? Well, it must somehow break up that pair. So they said, well, maybe 1s, 2n, 2p. Well, maybe one of the electrons gets promoted up into here in what we would then call an excited state. Now we have 4 unpaired electrons. Now we can possibly form 4 bonds, a hydrogen coming in. But if we look at the geometry of the orbitals, we have, I'm not going to do the 1s. There's the 2s, and then we have our 2p, x, y, and z. We got 1 electron here, 1 electron here, 1 electron here, and 1 electron floating around there. So the hydrogens could come in and try and overlap there, overlap here, but these p orbitals are going to make it very difficult for a hydrogen to come in and try to overlap here. Just, it's crowded, it's just, you know, this sphere is covering everything, whereas the p orbitals are all right there. It's just not conducive for that to actually happen. Also, there would be 3 bonds with a p orbital and 1 bond with an s. They're going to have slightly different characteristics. Turns out that all 4 bonds of the CH4 are exactly the same. Okay? So that doesn't exist. You might need to keep turning. So, here's our current theory. Okay? That we end up going, well, let me just do it this way. Well, I'm in trouble. I'm not even going to put that one on there. 4 equivalent hybrid orbitals. We'll call it sp3 hybridization, because the s in all 3 of the p orbitals are involved in the hybridization. So you're going to end up, you've had 4 orbitals to start with, you have 4 orbitals to end with. Notice that the energy, I tried to make it right in between the s and the p. Okay? Now, when that happens, you get 4 orbitals that are going to just get as far apart from each other as possible. You got the carbon atom right here. Each of the red corresponds now to my hybrid sp orbital, a hybrid orbital. All three of the p's and the s. Now notice that they're all the same shape. And we're going to have to kind of do 2 things hand in hand here. We're going to talk about the type of hybridization, but then we're going to talk about the shape as well. Okay? Because hybrid orbitals are always going to try and repel and get the maximum distance apart. And in this particular shape, it's the maximum distance apart. And this shape is called a tetrahedron. Okay? And is it, we no bells again today? There we go. All right. We'll go into more of that when you come back.